Hi, in this video, I'm going to give you an overview of the linear regression module and kind of a brief overview of the lecture notes on linear regression. So with all the modules, start out with the README file. It lists in here the readings for the week. And I've also given a suggested reading priority list. I'd probably start with the notes that we're going to talk through in a second. The things to know about regression. The second document was a document one of my professors gave me in grad school. I thought I found it, and I thought it would be it's a good document to share. Kind of goes over some important points on some important things to kind of know about regression analysis. So I thought I'd share it. The Tabachnik and Fidel chapter is a great overview. They go into a lot more detail. You can see the the math that's going on behind the scenes also in that chapter. And the things to know about regression gives you some of the formulas in there as well. And then there are a few other additional readings that if you need some additional or supplementary information, I've supplied that as well. So you can download those, a zip file here for it. You can also link to my notes on the main page and a link to the things to know about regression on the main page as well. There's an example walkthrough of conducting and interpreting a regression analysis in SPSS. The video got broken into two parts. So there's part one of the video and part two where I'll walk through both a standard multiple regression and a sequential or block entry regression analysis. Here are just a list like the steps for conducting a multiple regression analysis in SPSS. So you can see, click on Analyze Regression Linear and follow along through these notes, depending on which kind you want, which kind of regression analysis you want to perform. Here is my example and where I've annotated the output. So you can see this is, and I go over this in the video lecture on it, but you can see I've annotated all of the output of what kind of you're looking at, what each table is telling you, and kind of what the numbers mean. So you can look at that there. Here's the data set that I use in the example and an example write-up of both standard multiple regression and then a block entry regression analysis. This week, there is a discussion post where I ask you to go out and find an article in your field of study that uses multiple regression and to read the article and critique it. So you can read through that. So don't forget about the discussion post activity. And then as always, there is a data analysis assignment and a quiz on regression. Let's look, we're gonna kind of walk through the notes for a minute. So ordinary least squares regression, or OLS regression for short, is probably the most common type of regression analysis. And you'll see in here, I'm not very consistent with the terminology. You'll see it called linear regression, standard multiple regression, just multiple regression. Usually when anybody's just referring to like a regression analysis and they're not really specifying what kind of regression analysis, they're probably talking about an ordinary least squares regression analysis. It's called ordinary least squares because it uses the method of least squares to fit the regression line to the data. So if you imagine like a scatter plot, It's just a bivariate scatter plot. The regression line it's fitting through the method of least squares minimizes the distance between each one of those points in the line. So that regression line represents the line of best fit by that each one of those points is minimized by their distance to the line. And that's where the name comes from. You'll see in here, there are many different types of regression analysis. OLS regression is appropriate when you have your dependent variable is continuous, so it's measured on an interval ratio scale. And the independent variables can be either continuous or categorical. It doesn't matter. So there are other types of regression analysis. So the next module, we'll talk about logistic regression, which is used when your dependent variable is dichotomous. So maybe it's like a yes, no, pass, fail situation. You would use a logistic regression in that case. And the independent variables, again, can be either continuous or categorical. If your dependent variable has multiple categories without any order, you'd use a multinomial regression. If you have count data, like the number of children or the number of times this activity was performed, you could use something called like a negative binomial regression. So there are all kinds of different regression models, and we're going to cover the two of the most popular types. There are two main uses of regression analysis. They're mainly used for prediction purposes. So we're trying to use all of these independent variables to predict some value on some outcome. So like, we may try, an institutional research office on campus may try to predict first year students' GPAs using their incoming ACT score, their socioeconomic status, their high school GPA, some type of measure of motivation, to try to then predict how successful they may be in college. Predictions becoming a very big part, as a very big use of, I guess, for lack of a better way of saying it, of regression analysis. You think of like Amazon, you click on their site, they use all kinds of different types of fancy regression models to try to predict what you're going to buy, what type of ads to show you. So a lot of companies are using all of this big data that they have to try to predict consumer behavior, and they're doing a lot of that through different types of regression models. What we're going to talk about is the use of regression for kind of explanation purposes. This is really what's used in academia. This is where regression analysis is used in research. We're trying to understand why some phenomenon varies. We usually have like a theoretical or conceptual basis for the relationship among the variables. And we're trying to understand that relationship or test some type of theory about the reason why these variables are related in the way they are. You'll see this is what you would call like the regression equation. If you remember, it's just an equation of a straight line. If you remember from like 5th grade algebra, y equals mx plus b. This is the same thing. We're kind of extending it to have more mx's, I guess, in that equation. So y is our predicted outcome. Beta naught here is the y-intercept or the regression constant. So if you think about it on a Cartesian plane, it's where it crosses the y. This is the point where it crosses the y-axis. These other betas, so B1, this would be the coefficient for this first variable, x1. And then the E here are your error terms, or the residuals from the model. We're going to talk a little bit later about two different kinds of regression coefficients, unstandardized and standardized. And not to try to confuse you anymore, but a lot of times we refer to standardized coefficients as SPS refer to them as a beta parameter. And you'll see them called betas. Here I'm using the term beta is also used to represent a population parameter for a coefficient. So in this case, these are still unstandardized coefficients. These are just a population estimate of the S. So just not to confuse it with a standardized coefficient. That's what I'm trying to note here. So the null hypothesis in regression analysis can really be thought of. We can really think that we're testing two different kind of null hypotheses. One could be whether we're explaining a significant proportion of variance in the dependent variable. So, does the linear combination of independent variables explain a significant proportion of variance in the dependent variable? So we can think of that as testing whether our R squared value is different than 0. R squared is just like eta squared or omega squared. In an ANOVA model, it tells us the proportion of variance explained. So the F test that we have in regression can be thought of testing whether we are explaining a significant proportion of variance. So whether that R square value is different than 0 or not. We can also think of it similar to how we think of the F test in a ANOVA model, that if we reject the F in the ANOVA, it's saying that some of our groups differ. We could think of the same thing, that there's a significant relationship between our at least one of our independent variables and the dependent variable, right? So the null hypothesis is that all of the population coefficients are 0, against the alternative that like one of the population coefficients is different than 0. So there is a statistically significant relationship between the independent variable and the dependent variable. I talked a little bit about the R squared value, how it's similar to eta squared or omega squared in ANOVA, so it's interpreted the same way. You might also see it called the coefficient of determination. That's just another name for the R square value. And again, R squared tells us the proportion of variance in the dependent variable that can be explained by our set of independent variables. SPSS will also report what's called an adjusted R squared value. And basically the adjusted R squared value just kind of penalizes the R squared value for the number of predictors you have in your model and for your sample size. You can kind of think of the relation same way that we would compute eta squared and omega squared in an ANOVA model, and the omega squared was always a little bit lower than the eta squared. That's the same thing that's happening here as well. The adjusted R squared is more like the omega squared calculation in an ANOVA, and in certain situations they're actually congruent. So there are two different kinds. So our regression coefficients, those are the betas here in the regression equation. We're going to get, there are two different kinds of regression coefficients. And these really explain the magnitude and direction of relationship between the independent variable and the dependent variable. And so you can either report them as unstandardized or standardized coefficients. SPSS by default will print both of them for you. The biggest difference between them is the unstandardized coefficient is in the original unit of metric, and it's interpreted as, so a 1 unit change in the independent variable corresponds to a B unit change, whatever that coefficient is, unit change in the dependent variable. So like in this case, the unstandardized coefficient is -0.5. So that's saying that a 1 unit change in the independent variable corresponds to a 0.5 unit decrease in the dependent variable. It's a decrease because this was negative. If it was positive, it would be an increase. We increase on the independent variable, we increase on the dependent variable. Same way you would interpret a correlation coefficient. We also usually talk about the different when we have more than one independent variable in the model. We typically say like controlling for the other variables in the model, a 1 unit change would correspond to a 0.5 unit decrease, holding the other variables in the model constant. So we're saying, you know, what is the expected relationship between the independent and dependent variable after we've already taken into account the relationship among all of the other independent variables. So the unstandardized coefficient is in the original units of metric. The standardized coefficient is in standard deviation units here. So this is basically the regression coefficient we would receive if we standardized all of our independent variables and our outcome variable. So it converts them all into standard deviation units. So, you know, if our standardized coefficient was 0.15, then that would say, a 1 standard deviation increase in the independent variable would correspond to a 0.15 standard deviation increase in the dependent variable, holding constant all the other variables in the model. So, so where the unstandardized coefficient is in the original units of metric, the standardized coefficient is in standard deviation units. The intercept or regression constant, you'll get a coefficient estimate for it. We usually don't interpret it. It's really only meaningful when all of our independent variables are zero. Basically what the constant is the estimated value of the outcome when all of your independent variables in the model are 0. So unless 0 is meaningful for all of your independent variables, then the value of the intercept is meaningless. So what was that prediction one here? So, you know, the intercept, if we're predicting GPA using SAT, using all these independent variables, the regression constant in that case would be the predicted GPA for someone who has a 0 ACT score, a 0 in this SES measure, a 0 on motivation, and a 0 high school GPA. So it's a lot of times a meaningless value. We'll talk about it in Stat 3. You can make some linear transformations to some of these independent variables to make that constant meaningful if you want it to, but it's not necessarily. It's just really just scaling the model. We'll say you'll hear a lot of times when we talk about regression analysis that we're controlling for other variables. And what we really mean by that is that we're really wanting to look at you know, the relationship between X and Y after we've kind of held constant all of the other variables in the model. So in the example here, I'm saying you want to look at the relationship between education level and income. We may also want to control for other factors that might influence income, right? So what are some other things that might influence income, like the age of the person, their occupation that they have, you know, where they live, you know, so, you know, we want to take those kinds of things into consideration when we're looking at the relationship between education and income. You know, the correlation, the total correlation between them is going to be a little inflated. You know, once we then control or take into account. So we're saying if everyone was the same age, the same gender, the same race or ethnicity, had the same occupation and lived in the same geographical area, what is then the relationship between age and income? That's sort of what we mean when we're talking about controlling for other variables. You'll see a lot of different terminology used, especially for talking about the independent variables. You'll hear them called independent variables, predictor variables, regressor variables, control variables, covariates. They're all really talking about independent variables. A lot of times, some people make distinctions between them. You know, if it's a control variable or covariate, it's not my main variable of interest, like an analysis of covariance. But you're really interested in the relationship between the IV and the DV after we kind of parceled out the relationship between the other covariates. So that's just something that there's some terminology to be on the lookout for. You know, some general rules of thumb for regression analyses. You'll see you'll want about 10, 20 subjects per independent variable. Some other citations here. A unique thing about especially regression analysis in SPSS is you can't directly enter a categorical variable in the model just as it is. And this really depends on the software program you use. Some of them will let you say, hey, this is a categorical variable, and you enter it. But SPSS doesn't allow you to. So you have to, any variable that you enter in the regression model, it's going to assume it's either a continuous variable or it's a dichotomous variable. So if you have a categorical variable that has 3 or more levels, you have to do something that's called dummy coding or indicator coding for the variable to represent the different groups. So in this case, we wanted to enter an individual's race or ethnicity into the model, and we have 1, 2, 3, 4 race ethnicity. So we'll need to you always enter the number of levels of the variable you have. So we have 4, we enter 1 less than that. So we'd have a dummy and indicator variable for people who are African American. Anybody who's African American will get a 1 on that dummy variable, and everybody else will get a 0. You can have a dummy variable to represent those who are Asian. So anybody who is Asian will get a 1, everybody else will get a 0. You have an indicator variable for anybody who is Hispanic. Anybody who's Hispanic get a 1, you get a 0 for everybody else. The reason you only need 3 and not 4 is we can identify who is white because they have a 0 on all 3 of these variables. So if you entered a 4th one, it would be redundant information and the model would kick it out anyways. I'm just bringing this up as kind of just an FYI. I'm not going to have you do any dummy coding in this class. I just kind of want you to know for the future, if you don't go into Stat 3, that if you do have a categorical variable, you have to think about how you're going to enter it in the model. And usually, in this case, we would typically call like white our reference group. And so the regression coefficient that we get in the model for the first dummy variable would represent the difference between African Americans and whites. This would represent the difference between Asians and whites. This coefficient represents the difference between Hispanics and whites. So you'd have to think about, well, which group do I want to compare the other groups to when you pick a reference group. Like I said, I'm not going to have you do this. We'll do this in Stats 3, but I wanted you just to kind of know about it, and you can read a little bit more about it in here. Tabasha and Fidel go into a little bit more detail on this next thing. There's 3 different types of multiple regression, or 3 different analytic strategies. We're going to mainly talk about the first 2, the standard multiple regression. And basically, it just means that we've entered all the independent variables into the model simultaneously. They're all into the model at one time. And then each independent variable is evaluated where we're controlling for all the other independent variables in the model. Another type of regression analysis is called like sequential, or I call it block entry regression. It's where we're entering sets of variables into the model at different times and assessing the relationship between the variables at each time. I think Tabasha and Fidel call it sequential. I like calling it block entry because you're entering a set or a block of variables into the model. You may also hear it called like hierarchical regression. And it's not to be, there's another type of analysis of like hierarchical linear models, and it's a completely different thing. So I don't like using the term hierarchical, but you may see that somewhere. And in this case, you usually have like a theoretical or a temporal ordering to the variables. You know, these variables came first, then this, and you're wanting to examine like how the effect of a certain variable changes after you add in different sets of variables into the model. So you can assess like how the relationship between that independent variable and the dependent variable changes as we add in different variables. I think if you're going to use a block entry regression, you need to have a good theoretical, logical, or temporal ordering to the variables. You can't just say, well, I'm going to put this variable in first and this one in second and this one in third. You should have some type of theory or some type of justification for why you're entering the variables in the model in that order. And you'll see in the homework that the order you enter the variables in the model matters and has implications for how you interpret the model as well. I'm not going to cover stepwise or statistical regression since we're mainly covering regression analysis from like an explanation standpoint, studying the relationship between variables. This is really more appropriate for if you're using regression for purely predictive purposes, and we're not wanting to explain, we don't really care about the relationships among the variables. There's an issue that it's usually not talked a lot about in especially introductory regression lessons, but multilinearity it has serious consequences for how we interpret the regression coefficients in our model. And basically multilinearity refers to how interrelated the independent variables are among each other. We want our independent variables to be highly correlated with our dependent variable, right? Because they're explaining variation in our dependent variable. But we don't want our independent variables to be too highly correlated among themselves. If two independent variables are extremely correlated among themselves, then it's hard to disentangle their relationship they have with the dependent variable. So it's hard to get a good estimate of what the coefficient estimate might be. So if you're using regression purely for predictive purposes, you probably don't care about multilinearity. You should care about building the best predictive model. But if we're looking to explain the relationship these independent variables have with the outcome, then multilinearity is something that you'll want to consider. Luckily, SPSS reports are not an easy-to-use statistic for this. There's the variance inflation factors. Basically, what the variance, or you'll see it's labeled VIF in the output when you ask for linearity diagnostics. Basically, the variance inflation factor basically takes each independent variable, regresses all of the other independent variables on it, and takes the R squared from that model. So, we subtract it from 1 and take the inverse of it, and that's the formula for the VIF. So it indicates how much our standard errors would increase compared to a model that the independent variables were completely uncorrelated. Usually the little rules of thumb you'll see if the variance inflation factors are greater than 10, that indicates there's some severe problems with multilinearity, and you'll want to stop and kind of assess what's going on there. If your variance inflation factors, usually I start getting a little worried when they get over 5. I'm trying to figure out, hey, what's kind of going on here. But definitely anything over 10 saying you have a serious issue. Over 5, I want to kind of try to start diagnosing what's going on. If your variance inflation factors are less than 2, typically we don't have any problems with multilinearity. And we'll talk in stat 3 about, different strategies you can use to deal with that if you do have multilinearity. I mean, you can drop one of the offending variables, try to combine them into a scale, use some type of factor analysis to reduce the items. We're not going to cover in detail, I'm not going to have you test any of the assumptions for regression analysis. I list them in here so you kind of know what's going on. We're going to spend a whole week in stat 3 going through testing regression assumptions. You really have to get a lot more familiar with syntax in SPSS to really do some of these assumptions, do justice to test some of these assumptions. But a couple of things to keep in mind is that we assume the dependent variable can be expressed as a linear combination of the independent variables. So might as well just graph, just do a scatter plot of the relationship between the dependent variable and each of the independent variables. If you're starting to see like a curvilinear relationship, then we'll have to account for that in the model somehow by either including a squared term or some other type of powered term. And then the rest of their assumptions really have to do with the residuals or the error terms in the model. We assume that the residuals are normally distributed with a mean of 0 and a constant variance. That's what we're saying here. They're normally distributed, a mean of 0 and a constant variance. The constant variance assumption is the same. You might hear it called like homoscedasticity, and it's very similar to the homogeneity of variance assumption in ANOVA. So you can sort of read through here also some other important data considerations. Our dependent variable should be continuous. And if we're wanting to make inverses back to a population, then we should have a random sample from that population. So you can read a little bit more detail about that. And then the last part of the notes, I sort of try to just demonstrate to you how pretty much a lot of the statistics that we've talked about thus far, like from stat 1 and several from stat 2, are all really a special case of regression analysis. Actually, everything we've talked about in stat 1 and 2 are all just a special case of the general linear model. And so here I'm just trying to show you this is how you could do a t-test in a regression analysis and you get the exact same results. So they're mathematically, the math behind them is the exact same thing. So in a t-test, we're looking at the difference between two groups. Our outcome is continuous and our independent variable is binary. So you can read the scenario here and you can see my t-test output and then the regression output, and I've tried to highlight with these different colors how you come to the exact same conclusions because they're mathematically the exact same test too. At the end of the notes, I try to give you some additional helpful resources, some additional resources you might find helpful. Some other, useful videos. And these were just some fun songs. I thought they were cool. Regression is cool song, and then a linear regression song. They're just kind of fun to watch if you got some time to kill and you want some funny stat jokes, you can check those out. That's all I got for this module. If you have any questions, post to the message board, shoot me an email. I'm here to help. Thank you.